And I'll be recording this thing, like, and if like there's no technical issues, I'll upload afterwards, like both the notes and like the video. So we have a chat. So for people that like haven't done this before, so we have a chat part that you can like ask questions and everything. Also, you can like you can also oh, is my voice okay now? I'm hearing okay. You can also unmute and like speak to me, right? So if you have some question you want to ask, because like this is gonna be a review session, so this works best if you guys participate, right? So yeah, I can unmute anyone who wants to like ask something. Just you can either raise your hand or like mention in the chat area. So I'll be monitoring the chat part mostly. So some people might be down the list. If you raise your hand, I might not see it. But okay, so you, by raising your hand, I mean like there's a button there that you can like raise your hand if you have a question or something, or maybe mention in the chat area. Okay, so this is a review session, so I can do whatever you guys want to do. So let me just talk about the topics, right? So let me list the topics that are gonna be on the final. Okay, so I'll talk about the topics. Brian is asking about topics. Yeah, I'm gonna talk about topics. Okay, so let's see. So one is gonna be the conjugate beam method. Oh, okay. So let's say one is gonna be the moment area, right? Two is gonna be conjugate beam. Okay, so as mentioned in the emails, it's probably gonna be multiple choice on Canvas, right? So when it's a multiple choice, now it becomes a bit meaningless to like, we cannot like force you to use a particular method, right? But the question will be in a way that one particular method is much easier to use than the other ones, right? So in reality, you will end up with using a particular method. So Ronnie is asking no partial credit. So what do you mean by partial credit? Oh, okay. So you mean like solution wise? Yeah. So I would say no. There is no way that we can like check your solutions. But the thing is, there's gonna be more questions, right? So maybe there will be 20 questions or something, and like some of the questions are gonna be like simple conceptual questions, right? So for example, I don't know. Let's say just a simple dumb example, like what's like partial u partial p, is it like the second Castiglione theorem or the first Castiglione theorem, something like that. Yes. Okay, so the time of the exam will be the same time as the final, yeah. So 8 a.m. to 10 a.m. Yeah. So Michael is asking about examples of simple questions. I mean, the exam is non-existent right now, so the question, but I have some ideas how it's gonna be. So yeah, I'll give some examples of simple questions. About partial credit, so it's not final yet. We are just still working out the details, right? So yes, it's possible that we might ask you to scan your papers and turn it in on Canvas so that you get partial credit for your solutions as well, right? But yeah, as I said, like the details are not final yet, so things might change a little bit. But yeah, that's actually possible. Like, so we might actually ask you to scan your solutions and like upload on Canvas, so that you can get some partial credit as well. About grade distributions, nothing is decided yet. So for now, we are like assuming the default value, which is what we had from the beginning. All right. Did I answer all the questions here? Okay. Oh yeah, quiz 3 is also being graded and will be uploaded soon. Let me see where the chapter. Okay. Yes, a Spaghetti Bridge project is also going to be turned in on Canvas. I actually made an assignment for it on Canvas, right? So you have to upload your reports on Canvas. All right, so so yes, so what I've made on Canvas is a group assignment. So each group just needs to turn in one report, right? So you don't like just each group one report. Yeah. All right. So keep the questions coming. So I'm gonna move forward. So moment area, conjugate beam. I would say, if I remember correctly, unit load. Beam. Frame. Frame truss, right? So we have it for all of them. So will I be posting these solutions onto Canvas? So do you mean like what I'm writing here today? Oh yes, I'll post these on Canvas. Yeah. Frame problem. Okay. Okay. So yeah. So let me move forward with this. So yeah, I'll do some problems. Okay. So this is the third topic here. So we have the unit load method for all of them. So we have what, the Castigliano first and second, both for frames, beams, and trusses. And then we have 5. What's remaining? So we have influence lines. So this is gonna be for beams, which is most important, and then you have trusses. Right? Am I missing anything? That's about it, right? All right, so I'll try to like go over all of them to like just remind you of the main points of each of them and possibly do one problem for as many as I can. I probably won't be able to do all of them. So let's begin with influence lines, right? So this is because this is probably definitely gonna be there several maybe. So I'm gonna Do like so. Let's see. All right. So this is, I think, similar to what was done in class lecture. Right. So you have a beam like this. As I'm moving forward, if you see something you don't understand, you can either like unmute yourself and talk or write it in the chat area. All right, so that's the problem. Let me see. Yes. Okay, so we call them like, so let's say call this point 1. Let's call 2, 3. Let's call this 4. And let's call this 5, right? So you have all these points, right? So this is A, B, C, D. So this is your beam. So you can plot the influence line. So let's say for M1, right? What did we say the first step was? I call it like exposing the components, right? So if you want moment at 1, you have to expose the moment at point 1. So you draw the same beam, right? Right. So you do the, like you put everything the same way that it was. So if you want to expose moment at 1, you just have to, you can zero it first by putting like a pin here and then putting a couple of moments here, right? So this is moment at 1, this is moment at 1, right? So basically this is the same thing as the beam that you had. I just exposed the component that I want the influence line for. All right, so you have to rotate the beam in the direction of M1, right? So we have to have a unit rotation in the direction of M1. So you see, you can rotate it either to the from the left or from the right. The important thing is that the total rotation should be 1, right? So okay, what options do I have? So I can move this, bring this up, right? Nothing is preventing me from doing this. So when you come here, so for the right side, you can bring this down. I mean, you, for these problems, you can start plotting and going forward until like you run into an issue, right? So as long as there's nothing wrong while you're moving forward, you can keep going. So there are few criteria that you have to like keep in mind. For example, you have to pass through the supports, right? So you can't detach from the supports. The other thing is that like this angle should be 1, right? So here is a pin support, right? So you can only break the beam at pin supports, right? So you know I have to pass through this point, and also you have to pass through this point. All right. So I have a question that why did I put a hinge between A and B, right? So as I was saying, like the first step of our influence line plotting is that we have to like expose the component for which we want the influence line, right? So if I want the influence line for moment at 1, I have to like somehow bring out the moment at 1, right? So basically I put a pin here and I put its moment explicitly there, right? So it's the same thing as the continuous one, right? But the pin here with these two moments, right? With these two moments, basically it's doing the same thing in the original beam, right? I just brought the moments out and put the pin there so that I can rotate the beam at the place of the pin and plot its influence line, right? Does that answer your question, Adiba? Okay. All right. So you have a unit rotation here. So here's the pin and here's the support. So I know that I have to pass through these 2 points. So I come here. So again, you can break it at the pin, right? So you come down here. So I have like there's nothing wrong here, right? I haven't like detached from any of the support points. Everything is linear. Okay. Someone here asked for indeterminate beam. So you see, this is linear because it's a determinate beam, right? So if it was indeterminate, you could have curved the members, right? So for determinate beams, only for determinate beams, you have like these straight members, right? Okay. I'll also do an indeterminate one after this one. So someone's asking, look for a moment after the hinge at 0.5. Change if you expose a moment after a hinge. After a hinge, do you mean like somewhere like immediately after the hinge, for example here? Is that what you mean? I'm not sure if your name is shown here correctly. Magano, is that correct? Okay, between hinge. Okay, so you mean somewhere here. Oh, how do I go back? Okay, so you mean somewhere here, right? Okay, so let's call this 0.6, right? So let's draw the influence line for 0.6. So let's say M6, right? So you put everything as it is. You have this pin here. So what you have to do again, like the first step is exposing the moment, right? So you put a pin. This is basically the same thing as the original beam, but you've just brought the moment out in the open explicitly to be able to like rotate the members, right? Okay, so if I want to rotate, what do I do? So I rotate the right side first. Let's see what happens. So I know that I have to pass through this point, right? So I come down here. And I know that I can break at this pin, and I know that I have to pass through this point. So there is just one way to go. And there is nothing wrong with this, right? All right. So what about the left side? So let's try something. So I mean, I'm not even sure what the left side looks like. So I try stuff. Let's just keep it straight. So I see that if I want to keep it straight, I have to like draw something like this, right? But this is not possible because this member, you see, this member has to remain straight. Because you have to pass through this point, you have to pass through this point, and there is only one way to do it, by remaining straight. So I know how this segment looks like. So there's one way to do this, is to like plot it like this. And then this angle is gonna be 1. Does that look good? Did that answer your question? Oh, an angle of 1, it means just a unit rotation. Angle of 1 is unit rotation. You can look at it as 1 radian, right? So yeah, that's basically it. So Fiona is asking, do we need to write the maximum moment, numerical number? So what do you mean by maximum moment? Do you mean like this value? Okay, I would say yes. I would say yes. Write the values of moments at like extremities, right? So let's see how we can calculate this here. Can we calculate this here? So we have to calculate it from the angles, right? So this is a equilateral, like not equilateral, but like what do you call a triangle that has like these two equal? I think it's called. Anyone know what you call when a triangle has these two sides equal to each other? Isosceles, yes. So it's an isosceles triangle, right? So we know that in an isosceles triangle, like this angle is the sum of alpha and beta, right? So when this is 1, it means that this angle is half, right? So this angle is half. So this value is L times theta, which is half of L, because this is L. So basically, you see, based on angles, you can easily calculate these extremities, values at the extremities, right? Okay, so this is the story about the determinate beams, right? Any questions on influence lines for determinate beams? Did I miss any questions here? You can also talk, I mean, if you want. Oh, okay, okay. So, okay, I have some, okay, okay. So someone is asking about the fixed wall end of a cantilever, like homework problem. Would be replace the fixed end with a hinge tip. Okay. So now we go to influence line for indeterminate beams, which is what you're mentioning. Indeterminate beams. So you have the homework problem, which is like this, right? So let's call this A, B, C. For indeterminate beams, you can have curved segments. So you see, unlike determinate beams that everything had to stay straight, for these ones you can have curved segments. So as you mentioned here, so if I want like MA, exposing the force is basically the same again. So if I want to expose the moment at A, what I can do is like put a pin there. So basically in your head, you can imagine that I'm first zeroing the moment there and then putting its actual value. So if I do this, right? So there's a moment here. And so I have basically exposed the force. So for these indeterminate ones, this is just qualitative. So all we can do, we can like plot a qualitative graph. So you can't anymore like put actual values on there. So if you wanted actual values, you had to like solve an indeterminate problem. So, but the procedure is the same, but now you can curve the members. So if I rotate, again, you have to have a unit rotation because it's a moment. So if I do this, so you see, it's very gives you a qualitative sense of how things look like. So again, like this has data equals 1, right? So let's do like RA. All right, so after this one, I also do a inference line for trust. So let's say RA. Again, expose the force. So if I want to expose the force, I first zero it, and then I put the load on it. So if I move this up by a unit value, so I get something like this, right? So let's do one more, just if I put E here. So let's say M at E.
Ollie?
Yes.
For point A to B, is that a straight line for reaction A, or is it curved?
A to B. Okay, so it's curved, right? I didn't like, you can imagine it's curved. Yes, right? So this is also a curve.
Okay, thank you.
Yeah, sure. Nice. Thanks for talking. I like that. Yeah. So, okay, so let's do ME and then we move to a truss. So, again, exposing the force, it's the same. So you have a point E. If I want to expose it, so I just put a pin. I put ME. Right. So how do we do this? So you see, you have to have a unit rotation in the direction. Again, it's the same. The principles are the same. In the direction of ME. Right. So if I want to move this in this direction, so this left side is basically a cantilever, right? This right side is again like a curve like this, right? Basically, that's the, you can basically imagine that you're putting a moment here and trying to deform the beam using that moment, right? Or, I mean, or you're trying to have a unit difference in rotation. But how you achieve this difference in rotation is by like putting a moment there. So basically this difference is again the unit value, right? So any questions on inference line for beams, indeterminate, determinate, and stuff like that?
I have a question.
Yes.
So in the homework, there's a unit load going down for the first question. How does that affect this?
Oh, this one? Oh, that, I think that unit load is just to guide you, you
Okay.
know? Yeah, just to like remind you of the definition of inference line.
So it doesn't affect it in any way?
No. I mean, the procedure you use to plot it is just like this.
Okay, thank you.
Yeah, thanks. All right. Other questions? All right. So let's look at the influence line for truss. So the influence line for a truss. I'm just gonna use very simple one. right? So let's call this A, B, C, D, E, F. Okay, for inference line in trusses, oh yeah, so the trust one in homework basically is the same principle here. That one is just longer, right? So if I mention how we do this one, it's easy to like generalize to that one, right? Or I can even do the one in the homework. There's no problem there. So let me just bring it up. Where is my, let's see. Let me find the, all right. No, this is not the one. This is the one. All right, so this is the trust from the homework problem. So let me see if I can just quickly, to save some time. Okay, it's not pasting for me. Okay, you know what? I'm gonna do it. All right, so let's say I want the influence line for this one, right? This is the trust. So we have to basically go back, new page. So we have to go back to the definition of influence lines, right? So for trusses, this Muller-Breslau thing that we did, like unit load, unit displacement, like rotation, right? This is not applicable to trusses, right? For trusses, you have to just use the definition. So for trusses, the question has to tell you like, what's the manner of application of this unit load, right? So the question could be asking for unit load for like the moving load along the bottom segment, like this side, right? Or maybe it could be asking you for the top segment, right? So here it's asking for the load moving on GL line, which is this top segment, right? So this is not the one. So basically you have a moving load on the top segment, and for these trusses, you apply the load only at the nodes, right? Okay, so let's see. So basically this is the procedure. You apply the unit load here, right? You do a full structural analysis and find the force in a particular for a particular component, right? So I could say, in a way, exposing the component is kind of the same concept as we had for beam. So let's say FHB, right? So FHB, which is HB, okay, this is HB, right? This member. Don't do the zero force member before putting the load. This is important. Don't find zero force before putting the load, right? So after I've put this unit load here, I can see that, okay, now I can say I can start solving the problem. Like if I want FHB, so this is 0, right? And you know what? You're done, because you just want the force in this member, right? Because you're plotting the influence line for this member. It means that you put the unit load at different places, and each time you find the force in this member. So you don't need to go about solving all the problem, right? So that's step one. So you're done, right? So you remove this, you basically reset the problem. So you start from the beginning again. Now this time you put the unit load here. You see, this is again zero force member. Then you put the, okay, so you, when you want to plot it, you plot this. So this is basically the x-axis is the position of unit load. So I saw that when my unit load is here, the value is 0. When my unit load is here, the value is 0. When my unit load is here, the value is what? This is a zero force member again, is 0. So you can see that for member HB, no matter where I put my load, the values are 0. So basically the 0 line is the unit load for HB. But the situation is, so this is the unit line, the unit influence line. So this is FHB influence line, right? So what if you want it for like another member? So let's say, let me quickly plot it. 1, 2, 3, 4, this, this one, this one, this one, right? So this is G, H, I, J, K, L, A, B, C, D, E, F. And we have a support here. We have support here. Okay, let's see.
Ali, just can you hear me now?
Yes.
Ali, just a quick question before you move on. In terms of the format, since it's going to be multiple choice and you want us to draw influence lines, is it going to be like the professor's going to give us 4 different options and we have to choose the right one?
Yes. So maybe we give you like, we say, okay, what's the correct influence line for FHZ, right? And there is like 4 graphs there.
Okay, so the 4. Okay.
So what you have to do is basically the same. You just have to solve the problem. But for sure, like the problems are going to be simpler, right? So it's not going to be like long like this. So they will require like shorter solutions, right?
Yeah. Okay.
Yeah.
That's quick. Okay. Thank you.
Yeah. Sure.
Thank you.
Yeah. Sure. All right. So. Okay. Just. Okay. Are there any questions right now? About the score, someone is asking, since it's multiple choice, are you going to get your scores instantly? So as I said, like the details, we're not clear yet. So if you want to, so I'm not sure if you are going to get like scans of your solutions or not. So if we end up like not getting the solutions, like there's no partial credit, which is not bad. Like if we end up doing that, it means that like the questions themselves are going to be simpler, right? So there's going to be more questions, but simpler questions. So then, yeah, you would get your results like instantly, right? If there's no partial credit, which I think would be beneficial to you guys, like because like that way everything is simple and easy. But we'll see. Like it's not final yet, the details.
Ali, quick question.
Yeah.
So for that problem you just did with the truss,
okay.
Did you know where to put the unit loads?
Oh, okay, that's a good question. So you see, the question is gonna tell you, like the question is guide you about like how to apply the unit load. So you see this line, the load is moving on GL line. So this means that like you have to apply your unit load at these nodes, right? If it said that the load is moving on AF line, then you had to like apply your unit loads here.
Oh, okay, so then you would need to put a unit load at G, H, I, J, K, and L, correct?
Yes, exactly.
Okay.
Exactly.
Okay,
So,
thank
and
you.
that's what I did. So you have to put the unit load at each of these and calculate the force in that particular member or for that particular component. I mean, you could be asking for influence line for reaction RA, right? So each time you put the unit load, you calculate the reaction if you want the one for reaction, which is like mentioned here, right?
Mhm. Yeah.
Does that answer your question?
Yeah, thank you.
Oh, okay, sure. All right, so let's take a look at like the influence line for HC. Right now, okay. Now you have to like regular truss analysis. You have to like find the force in HC each time. So let's put a unit load here. If I do that, so you start like solving the problem based on this unit load. This is gonna be 0. I use the cut method. So you cut the structure here, right? So what you end up with is something like this. There's gonna be FHC, some F here, some F here, 1, 1. So what do we have here? So if I write sigma Fy equals 0, I get FHC, like cosine, like let's say sine 45 equals 0, because in the y direction I only have the vertical component of FHC. So this means that FHC is 0, right? So again, what you get based on this, let me move this down. So if this is my influence line graph, so when the unit load is here, so this is the position of the unit load, right? Position of unit load. So when the unit load is here, the force in HC is 0. So this is one point. So basically you're doing it point by point. So I move the unit load here. So let me see if there's any questions so far. Okay, there are a bunch of questions. Okay, so let's see. So first, Alvaro is asking, will the result be the same if you apply the load from A to F? I would say no, definitely not. Because, so let's look at, for example, HP, right? Let's look at HP. Do you remember last time everything was 0? But if your unit load is put here, the force in HP is no longer 0. So it's very important, like you have to specify what kind of influence line are you calculating, like where are the unit loads applied, right? And it's like up to us to like tell you which nodes you have to consider, right? So yeah, the result is definitely gonna be different if you move the unit load on the bottom side compared to the top side, right? Okay, for the influence lines, line of HB, how come is 0 when the load is at H? For the, okay, for the influence line of HB, how come it's 0 when it's at when the unit load is at H, right? So basically you can, it's just a truss analysis, right? So the reason a member has a particular force is always what? Because you solved it and you found out that the force in that member was that particular value, right? So basically, when you after you put the unit load at the nodes, it's just a regular truss analysis, right? So when you have this problem, That's like with this unit load here, right? So you can see that this is zero force member because of the particular form of this node. So this is one of the situations that we said we have, like if you have two members alongside each other, third one is zero force. So yeah, basically that's by recognizing that this is a zero force member, right? Okay. Okay, is this still zero force? Okay, I think I answered these questions here. Any other questions on this? Okay, so let's move forward. So basically, again, you just have to put the unit load here and there, like at the positions that it should be, and then solve the force in a particular member. So now I've moved my force here. So now the reaction changes, right? The reaction is no longer 1. If you find the reaction, you will find that this is 2/3. So it's just, again, like a regular truss analysis. So you have to find the reaction and then the forces. So, all right. So if I bring out, the left side here, so this is gonna be this is gonna be the unit load. This is gonna be some force. This is gonna be HC. This is gonna be again some force, and this is gonna be 2/3. Okay, now if I write sigma Fy, so I would say -1 minus FHC, like sine 45, plus 2/3 is 0. So FHC is equal to negative. Yes.
Quick question. So if you were to move the unit load over to I on top of the truss, would the influence line still be 0, or would it actually be, would it be non-zero? And would it be 0 if you were to put it at C?
For the same HC that we are looking at right now?
For the IC. So you know how you discussed that you put the unit load on top of the member HB? Like the unit load will be distributed along the diagonals, therefore making the influence line 0. Correct?
Yes. Yes, because like we are looking at member HB.
HB, yeah. But what if you're looking at member IC? Would it matter? Like, would the influence line be non-zero if you place it on top, and would it be 0 if you place it at the bottom?
Okay. So let's say you're plotting the influence line for member IC, right?
Yes.
So when you're plotting for IC, if your unit load is here, what's the value?
What?
So let's just do it quickly here. So if I do IC, so what's the value of force in IC right now? So you see, this is a 0 force member, right? For this problem.
Correct.
So this is 0.
Okay.
Now, if you move it here, it's still for this problem also a 0 force member. But when you move it here, you see the force in this. If you solve this problem, like you write equilibrium in this node, you will find that the force in this is -1. So this is gonna be like this.
Okay.
Right? And then you move it here, and any of the other points is gonna be 0. So this is your influence, right?
Would it matter if you put it down at point C? Like.
All right. So yeah, let's say the question was asking for like the bottom side, right? So then for IC, right? For IC, no matter where you put your unit load, this is always gonna be 0 force member because this is 0 force member.
Okay.
0 force member, right?
Okay.
So
Makes
again,
sense.
for IC, when the unit load is moving on the bottom side, you would get a 0.
Okay.
Right.
Thank you.
Yeah, sure. All right, so FHC is gonna be square root of 2 over 3. I hope I didn't make a mistake anywhere. C is 45. So you see now when we are at this position with the unit load, we're gonna go down negative square root of 2 over 3, right? And then you continue, right? So you put the unit load here, you again do the analysis, you find the force in HC, and you plot it on the graph. This is the basics of it. There's really not much here. So questions? Any questions you have, you can ask. So we did one influence line for determinate beams, we did one for indeterminate beams, and we also did one for trusses, right? Maybe. Yeah, I'll post the notes on Canvas. I think I'm also recording this. I might also upload the record. Well, all right. Any suggestions what we should do now? Problems? I mean, it's online, so I can continue, right? So I mean, technically we are at the end of the class, but the good thing here is that like no one is gonna throw us out of this class, right? So I'll be continuing until like the next people join. So Ron is asking, does the influence line for HC start at point G or H? So you mean like where does this line start? Like this line? So basically what you do is like you find the forces at like these discrete points. So you have a bunch of points, right? So for example, you find that at this point it's here, and then you connect them. You just connect them, right? With like straight lines. So you have found that at this point it's 0. So you already have a point here. You have found that at this point, at like point H, when unit load is at H, it's at this point, right? So you connect them after that, right? Does that answer your question? All right. So someone mentioned we should do one. All right, let me save this one. Save as. All right, so let me see. Okay, we're back here. Back here. Oh no. Okay, here. Good. So we have 2 requests, like second Castellano and to unit. Frames. Okay. Unit load and second Castellano. So let me see which homework was on second Castellano. I think it was homework 7, right? So guys, let's have a 5-minute break. right? So that like people from the other, so people from this class can like stay if you like. So at 2 we have probably some other people joining. So we'll take like a 5-minute break and then come back, right? I'll restart at 2. So I'm not gonna disconnect or anything, so you can stay if you like. So I'll be back like in 5 minutes. All right, I'm back. All right, let's see. What's a Discord party? All right, so let's see if what's happening. Choices. Oh, okay. Discord party. Oh, I see. Right, yeah, reacting to messages would be a nice idea. All right, so let's see what other, so people that have joined for the second class, so basically I'm gonna make this a continuation, the topics that we covered on the first part. I mean, I've recorded this, right? So it's I upload the link. You can like see the video of the material that we went. I just did some influence lines for the first part. So now we're gonna focus more on deformation stuff, and like I'm seeing that people are requesting that, so that's good. Okay, so let's see what topics do we want to cover now. So second Castigliano. So I'm gonna do this for a frame first. The unit load for frames. Unit load for frames. Okay. And then I'm gonna, for unit load for frame, maybe we can do the midterm, like the quiz 3 one. Right, I'll do this one. And first Castellano, I'm gonna do the quiz 3 one. All right, so Brian brings up a good point. Will you like be able to like write down formulas for yourself, or maybe even like use your lecture notes and stuff? We have not decided on that yet, right? So there's a way to do the exam like with the proctor and stuff like that. So if you decide to do it like that, then you won't be able to use your notes, right? So I would say that the safe thing right now is to like assume that you won't be able to use your notes. But for first Castigliano's theorems, definitely we're gonna like give you the equations if you need them. So those big ones. So second Castigliano. All right, so let's start with the second Castigliano one. Let's find a good problem. Like what should we solve? Let's do one of these spring ones. I think I never did this one in class. Yeah, this looks good. Do you guys like this one? So yeah, I want to do 1 second Casimir. So I've seen in your exam from your quizzes that some people are a bit confused what's like which method is what, right? So before jumping into more complicated homeworks and stuff, try to use just the simplest examples you can, just to make sure you understand the methods themselves, right? So always start with very simple, like simplest possible examples. Like just draw yourself a cantilever and try to solve it with all these methods and check if you get like the same answer or not. That's always the best strategy, to like start with like the simplest stuff. So yeah, let's do this one. So it's what do we want? Deflection at P using the second Castellano's theorem. Okay, let's do this. So we have this thing, right? So this is Ks. There's a load P here, right? Here's a load P. All right. So this is L and EI. This is L and EI, right? Okay, let's do it. So we want to use second Castigliano, right? So just for yourself, write this thing. So see, this is the first. So this is first, this is second. So basically the first one says that u should be a function of delta 1, delta 2, or even delta n, or rotation 1, rotation 2, right? So here you see it's a function of externally applied forces, right? So this is the second one, is about writing the energy as a function of forces, Oh, okay. So someone's asking what are we solving for? So A, B, and C, we want for delta B, right? Using second Castiglione. So the second one, this is a function of externally applied loads, right? Like you can have M1, M2, and N. So distinguish the first one from the second one clearly. Make sure you understand that these two methods are different. So when you want to solve something using the first one, you use like formulas like EA delta squared over L, 2L. So this was for a bar, do you remember? So for the beam segments or frame segments, you had that big formula. So these are functions of deltas. But for the second one, how you calculate energy is that, so you say that, okay, I want this partial thing. So this partial thing would be the integral m partial pi over ei. So this is when you want to include like just contributions from moment. So if you want contributions from axial force, you have to like include this one as well. So remember that this is after the equation, after derivative, right? Differentiation, after differentiations. So u itself is just the regular m squared over 2ei plus n squared over 2ei, right? All right, so let's see. So you see, if you want, so again, I'm stressing that this is the second Castigliano. The second one is about forces, and basically you just have to find the moments and like axial forces in the segments, and like write energy as a function of forces, right? So basically I just have to find the moments. So this one is a very simple one. So if I do this, right, so there's a p here, so this will be p over 2, this will be p over 2. So if I take my x from here, and this is symmetric, right? So I just need one side. So m of x is px over 2, right? So how about the spring? So for the spring, again, I need the energy as a function of forces. I know that for a spring, whether it's like rotational or linear, it's like theta squared. So this is as a function of displacements, right? So I have to somehow convert it to some function of forces. I also know that like m is equals to k theta. Like it's like the Hooke's law, right? You have like the force displacement relationship in a spring is linear. So basically I know that theta is m over k. So if you substitute, you get half of m squared over k. So basically, this is the energy for a rotational spring. So I need the moment inside this spring. So moment at this point, so these are L. So moment here is PL over 2, right? So let me save this. Okay. So let's write the energy. Again, I repeat. So this is, I want delta. So I want partial U, partial P. You see this P. Partial U, partial P is equal to, so I want just the contribution from moments. So I do it like this. Partial equals the integral. I got the moment px over 2, right? Now I'm using this equation, so I just have to put partial m partial p, partial m, and this is just my m, right? Moment. Partial m partial p is x over ei. Now I have two of these because of symmetry, right? So I said it's symmetric. Okay, so you have two of these from 0 to L plus the contribution of the spring. Remember, so this is after differentiation. So I have to say partial p pl over 2 squared over k theta. So basically I substituted this one, right? So what does it turn out to be? So partial u partial p equals delta at b, which is equal to p over 2ei integral of x squared from 0 to L plus partial p pl squared 8k, right? So this becomes pl cubed over 60i plus L squared over 8k equals delta B. So this was basics of second Castigliano's theorem. So if you understand this thing, basically you can solve any questions regarding second Castigliano's theorem. Any questions about this? Okay, let's look at the quiz questions, right? Quiz 3. Open it like this. What was the first one? The first one was unit load method, right? Unit load method. I'm gonna start with what do you guys think? I think I never solved the homework, this quiz problem. Do you want to solve all of them? I can start from the beginning, like, because it would be like a review of unit load method, a review of like the first Castigliano's theorem, and like a review of unit load method for frames, right? Yeah, so I'll start with the first one. I wish I could copy this, but I can't. Gonna try. Oh, you know what? I'm gonna open it here. Oh, nice. Okay. All right. Let's solve this. So we want to use the unit load method, right? We want to find delta horizontal at delta vertical at H, right? So the procedure for unit load method is that first you have to solve the actual structure. Right? So it's just a regular truss analysis, right? So you find zero force member. So these two are 0 because of the form. So it's this form, right? You have like a kink, like a corner with no load. So again, this one the same. So after you find these two, like when you find 0 force members in your head, imagine like you're removing them. So if you remove them, these two also become 0. So that was easy. So what else? What else? What else? Is there any other 0 force members? Oh, I see one more. So you see, we had, I've mentioned this before, like we had this situation, right? So this situation is also 0 force member for this one. When there is no load here, right? No load here. So this is kind of equivalent to when you have like a support like this, that's like in the direction of this member, then this third one is 0. Basically they are the same, right? So that what this does is basically gives you one component of force, right? So which is in the direction of this member. So basically it's the same as this one. So I can say that since like this gives you a force in that direction, this support, right? This support gives you something like this, so this one is 0. I don't see any other 0 force members. Anyone see any other ones? I think that's it. All right, so now we have to just start solving the problem. So let me just draw it quickly like this. So I'm gonna remove those 0 force members on the right. So I'm just gonna put P and like this one, I, H, A, B, C, G, right? Okay, so some questions here. Would Hg be 1 since there is no horizontal force? Hg be 1. By 1, do you mean 0 force member? Oh, okay. So people are asking why is IH 0 and not Hg, right? So let's look at this corner. So basically, if you bring out the situation, it's like this. So you have one member, you have a pin support, which basically applies. So you see, this is a roller. That's the key difference. So this one applies like a force, like this. And like this becomes a third member. So basically, you have a situation similar to this one. So this is 0. Does that answer your question, Brian? That's why this member is 0. So why isn't this member 0? It's because of this support. So you see, this support is like this. So it has 2 components of force. So you see, it could have a component along this direction. So it's not a 0 force member, right? So that's the reason Hg, immediately at the beginning, you can't say Hg is a 0 force member. And that's why IH is a 0 force member, because of this, because this is a roller. Oh, that's true. So you see, after you do the analysis and you find that the horizontal force is 0, then you can say it's 0. But immediately at the beginning, we don't know if it's 0, right? But as we move forward with the analysis, we can say that, yeah, it turned out the horizontal component turned out 0. Yes, that's true. Yeah. All right. Nice. So let's move forward with the analysis. So if I have P there, so this is gonna be P over 2, this is gonna be P over 2, and like this one is gonna be 0. So now you can say that, okay, now you can say that this is also 0. This is 0, this is 0. You see, so after you find that the horizontal component is 0, then you can say, okay, that one is also 0. Now I see that this is symmetric, right? So I just need to find some of them. So let's look at node I. So node I is like this: P over 2, TIA, and like that's it. So TIA is negative P over 2. So this is negative P over 2. Let's look at node A. So you have P over 2 compressive coming from AI, right? So you have TAH, you have TAB. So if I write sigma Fy equals 0, so I get P over 2 minus TAH over square root of 2 is 0. So TAH is P square root of 0 over 2. AH P square root of 2 over 2. All right. So let me know if I make a mistake somewhere. Okay. So sigma fx, oh, sigma fx for A is 0. So TAH over square root of 2 plus, okay, so I know TH, okay, so let's say I know TAH is like, so I know P over 2 plus TAB should be 0. So TAB is again like P over 2. That makes sense, right? So these two compressive forces, you can just do a quick check. So these two compressive forces, and you have one tensile force. So the node A is at equilibrium. So all that remains is this node, node B. So if I do node B, so I have 1P going down, you have some P over 2 here, symmetry P over 2. So this is basically P. So this will be negative P. And the right side, the rest of them, because of symmetry, is going to be the same. Okay. That was the analysis. So you for unit load method, so we are trying to find delta vertical at H using the unit load method. So it's a unit load method. So you need to do another analysis, right? So you need to do another analysis where you put your unit load at the place and direction that you want the deformation. So we want horizontal at A. So we do this. We put a unit load here. So this is gonna be half. This is gonna be half. So you need to find the forces in members again. Like again, so this is gonna be 0 force. This is gonna be 0 force. Negative half. Right. Again, you have symmetry again, so you need to just find one side. So A, I, H, G, C, B. Okay. So let's look at node C. So there is half compressive, there is TCP, there is TCH. So TCH over square root of 2 minus plus half is 0. So this is sigma Fy, right? So TCH is square root of 2 over 2, right? So this is square root of 2 over 2. This is gonna be half again, right? So let's look at node B. Oh, we have one more zero force member here. This one is also zero force member because like at this node, there is no force now. Like before there was a P, but here there is nothing. And it's symmetric, so you're done. Basically you have 3 members. All right, I've seen some people like confused about like this formula that we have to use. So now you want to use the equation for unit load method, external work of unit load structure. Unit load structure is equal to internal. Okay, so let me write the expression for external work. So you see force times displacements, right? So the external loads are just these 3, right? You have these 3 applied as external loads, the reactions. So you have to just find out what's the displacement at these external loads, right? So the displacement at H for this one, so you have basically 1 times delta vertical at H. Let me write it in black. 1 times delta vertical at H, right? Plus, so the support, we have to look if we have any settlements, right? So you see you have 1 settlement here. So there is a displacement at the left support. So the settlement is coming delta S down, right? So it's in the opposite direction of the force. So you need to put a negative. So we say, okay, that the work done by the settlement because of the external load on the unit load structure is negative. Negative half delta S, right? And this one, like this support, since it has no settlement, it does no work, right? So this is your external work. So, okay, this is equal to the internal work. So the internal work, so you have what formula you have? So for you have for trusses, lowercase, uppercase, Li over Ei Ai. This is just because of the internal forces, right? It doesn't have anything to do with temperature or fabrication error or stuff like that. So this is just because of the actual internal forces that you have in your structure, right? So because E and A are the same for all members, you can take it out, right? So be careful that this L is not the same for all members, right? So for example, these members, these diagonal ones are L square root of 2, and like these ones are L. Yes, that's the correct answer from Karen. So the settlement is multiplied by half because of the value of this force, right? So it's multiplied by the external force that's applied on the unit load structure, right? Does that answer your question, Calvin? Okay, nice. All right, make sure you understand everything here, right? So we just have to multiply now each of these terms, right? So we have to each of these terms. I'm just writing each of these terms for each member. You just have to go member by member, and remember that if you have a member that is a zero force in either of them, like you see, you have these terms, right? Capital and lowercase capital, right? So if this is zero or this is zero, you don't need to write it, right? So let's see. For example, here. So you see these three members are non-zero in both of them, right? In both of them. And like they have the same values in four members, right? So you can chop it into two categories. So let's see. You have 4 of negative p over 2 negative half length L. Okay, let me write it like this. Everyone understand what I did here? Okay, Sam is asking, let's say the force, the reaction force was pointing down. So let's say the reaction was like this. You are correct. If like the reaction was in the direction of the settlement, then your work would be positive, right? So work, do you remember, like this is the expression for work. So this cosine theta is the angle between like the force and the displacement, right? So when it's like 180, it means that they are in opposite directions. If they're like in the same direction, then theta is 0, then you have a positive sign, right? Does that answer your question, Sam? Oh, nice. So everyone, do you understand like where did this 4 come from? Where did this one come from? Where did this one come from? So you see, I'm basically calculating n times, so capital N times lowercase n, right? So I'm looking at these members. So I see that. Okay. So in these members. So these are the 4 members I'm considering. So in the unit load structure, they all have a value of negative 1/2, right? So I put here. So this value is coming from the unit load structure and these negative 1/2. So I have 4 members, right? So these 4 members also, they have a value of negative p over 2. So I put it here. So I see that the value of n times n is the same for all these 4 members. So I multiply it by 4, right? So the same goes for the other members. So you have square root of 2 over 2. So now I'm looking at like this member, these two. So you have, again, like you have the same force for both of them. So you have square root of 2 over 2, and the force in the other one is p square root of 2 over p square root of 2 over 2. Right? So that takes care of like the effect of like internal forces on deformation. So all that remains is temperature and like fabrication error, right? So we say plus. The temperature effect is like this: L alpha delta T times N, right? So again, you have to sum it over all members, right? So here, only one member has temperature change. You see this AH, Are you talking about length? Length in which? Oh, okay, okay. So yeah, I forgot the length here. Thanks. So this should be L square root of 2. Nice. Nice. Yeah, thanks for mentioning that. So yes, so I have just one member, right? So it becomes L square root of 2 alpha delta t. The force in this one, so this one has delta t, right? This member. So the force in this one is what? Square root of 2 volt. And that's it. That's all you need to do for temperature. So if I move this down and move this up, plus fabrication error. So which member has fabrication error? This member has fabrication error. So fabrication error is easy. Like if it's like this, delta times square root of 2 over n. That's it. So basically delta times that's basically everything about this unit load method for trusses. Any questions on this? Let me see this. Questions on the unit load method? All right. If not, let's move to this one. So definitely you're gonna have some question like this on your quiz, on your final, right? So try to like understand everything about like this unit load method. So okay, so we solved one second Castigliano theorem. So this is gonna be first Castigliano theorem, right? So this is first Castigliano for truss, right? So all you need is the energy term for a bar, which is like EA delta squared over 2N. So this is elongation, shortening in a member, right? Oh, okay. So people are asking. So I'll have probably 2 office hours. So one will be on Saturday. I'll send an email about this. Like one will be on Saturday, like the 8 p.m. that we had. So the other one will be on Monday. The time on Monday, I'm not sure yet. So I won't have office hours today because like this session was basically like a review session. But so try to study as much as you can, and then probably either on Saturday or on Monday, if you have any like remaining questions, then we can do another like online one like this one. And you can like ask questions. Also, you can like share your screen. Like if there's something that you want to write, you can share your screen with me and I can like see what you're writing, and then I can help you with any questions and stuff. So yeah, I'll have a couple of more office hours before the final. One on Saturday and one on Monday, right? Okay, so let's do this one. So the first Castigliano's theorem, you see it's U, it should be a function of delta 1 to delta n or theta 1, theta n. So it's a function of displacements, right? So you have to label the total displacements of the structure, the total degrees of freedom that you have. I have seen like in the exam, some people like assign displacements to these fixed nodes. You see, so the pin supports do not move. So basically you're finding the degrees of freedom. So you have to see at which points your structure is free to move, right? So you have in this structure you just have delta 1 and you have delta 2. So this is the first step for first Castigliano. Remember, the first Castigliano's theorem is displacements. So you have to label the nodal displacements, the nodal degrees of freedom, right? So I'm gonna name the members. So this is 1, 2, 3, 4, 5, 6, 7. After you have labeled the members, you have to find out the members. You have labeled the members and the displacement degrees of freedom. Then you have to find out the elongation and shortening of each member, right? So I start from member 1. So you see member 1 is something like this, right? So you see there is no shortening or elongation of the member because both of its ends are like fixed, right? So there's nothing here. Member 2 is basically similar. How about member 3? So you see member 3 has this delta 1 here. You can bring these members out one by one. So if you find the components like along the member, so this will be delta 1 watt cosine 45. So you see we want the elongation of the member, right? So it's important like this degree of freedom in what direction it's moving the member. So if it was like we have a member that like the delta is perpendicular to the member, right? So perpendicular ones don't have any contribution to elongation of the member. So this will become delta 1 over square root of 2, right? So this is basically the elongation of members 3. Let's see, member 4. Member 4 is like this. Again, both ends are pinned, so there's no elongation. So this is member 4. Member 5. Member 5 is like this, right? So it's like this. And then you have this delta 1. So you see all of delta 1 is causing elongation in member 5. So basically it's delta 1 itself, like the elongation. How about member 6? Okay, member 6 is also interesting. So you see member 6. So there's a delta 1 here, but it's perpendicular, right? So it's perpendicular. So like delta, let's say elongation or shortening is 0, right? So the component of delta 1 along member 6 is 0. So the delta 1 does not have any component along that member. So let's see member 7. So you have delta 2. So this is member 7, right? You have delta 2. Again, the component shortening is equal to delta 2 cosine 45, which is square root of 2. All that remains is member 8. Member 8 is also interesting, right? So member 8, delta 2, delta 1. So delta elongation or shortening is delta 1 minus delta 2. So you see both ends are moving. So you have the difference in lengths of the member itself. It's like the difference of these movements at the ends. So now that you have the elongation for all members, you can start writing the energy. So based on this formula, right? So U is member 1 is 0. So member 3 basically okay, EA over 2, I bring this out. So Remember that lengths are different for each member. So I have delta 1 over square root of 2 squared. So this is member 3 over L square root of 2 plus 4 is 0, 5 is delta 1, length is L, 6 is 0, so this is 5 plus 7 delta 2 over square root of 2 square root of 2 L square root of 2 plus member 8 delta 1 minus delta 2 squared over L. So, okay, for member 8, Claire is asking, why is it delta 1 minus delta 2? So you see you have this member. Let's say this end is moving delta 1, this end is moving delta 2. So let's say after deformation, like let's say this point comes here, and let's say this point comes here. This is after deformation, right? And like this is the original length. So what we are looking for is the elongation, right? So basically this is delta 1, right? This is delta 2. So can you see that, like this is also delta 1, right? So you can see this is delta 1, this tiny portion here. So basically this thing that we're looking for is delta 2 minus delta 1. Do you see it? So imagine that, like if you had just delta 1, there would be a shift, right? So let me see if I can plot it bigger. I don't know if you can see it. Like, let me see if I can zoom. Do you see what's happening here? So if this is the original bar, if you shift it by delta 1, you come here, right? Shift it by delta 1, you come here. So if you shift it by delta, so this point moves by delta 2. Now part of delta 2 is delta 1. So if you take out that part, you end up with this segment, which is delta 2 minus delta 1. Oh, you're wondering about the sign. Okay, so you see the sign, you can make an assumption. You can make an assumption that like delta 2 is larger than delta 1, right? It doesn't matter. Why doesn't it matter? Because like you see in the energy, it's squared, right? So you can make an assumption that delta 2 is greater than delta 1, and then as you said, it becomes delta 2 minus delta 1. That's fine. Yeah. So it's kind of a like an implicit assumption that like you could make the assumption that delta 2 is greater than delta 1, and then it would be delta 2 minus delta 1. But the sign ultimately doesn't matter because like it gets squared here. Okay, nice. All right, guys, I think we are done here with this. So 8, so this is 8. So all you need to do is say partial u partial delta 1. Okay, let's first simplify it a little bit before. So let's see how we can simplify this. U is EA over 2 delta 1 over 2 square root of 2 plus delta 1 squared plus delta 2 over 2 square root of 2 plus delta 1 squared minus 2 delta 1 delta 2 plus delta 2 squared. So basically this one, this one, this one, this one, this one. So U is EA. Let's multiply everything by 4 square root of 2L. Delta 1 squared plus 2 square root of 2. Delta 1 squared plus delta 2 squared plus 2 square root of 2. This becomes 4. Plus 2 square root of 2 delta 2 squared plus minus 2 delta 1 delta 2. So U is EA over 4 square root of 2L times 1 plus 4 square root of 2 delta 1 squared plus 1 plus 2 square root of 2 delta 2 squared minus 2 delta 1 delta 2. Yeah, this problem numerically it's kind of ugly, but yeah, that's the way it is. Why is the displacement for member 6 0? All right, so you see for member 6, if you plot it like this, so delta, imagine delta 1 is a vector. So we want the component of delta 1 along the member. Do you see that this is perpendicular, right? So it has no component along the member. Does that make sense? Okay, nice. So let's see. All right, so now we have to like say partial U partial delta 1 is equal to its corresponding force. Where was delta 1? So delta 1 is here, right? So delta 1 is here. There is no force. There is no force here, so it's 0. Now partial U partial delta 2 is equal to P. So you see the same. So if you look at this node, it becomes P. All right. So that's it. You just have to carry out this ugly 2 equation to unknown. So EA over 4 square root of 2L times delta 1, 2 times 1 plus 4 square root of 2 delta 1 minus 2 delta 2. This should be equal to 0. Then EA over 4 square root of 2L times 2, 1 plus 2 square root of 2 delta 2 minus 2 delta 1 equal to P. Now you just have to solve this 2 equation to unknown. You can find, for example, delta 2 from here and then substitute in this one. And then find delta 1 and then substitute back in one of them and then find the other one. So let's assume that I have found delta 1 and delta 2. So you see the problem wants the force, right? So the problem wants the force in AD, this member, right? So AD was like this. So it had delta 1. So to find the force, you need this formula, right? So the force is EA delta over L. Now this delta is like elongation, right? Or shortening. Now, if you find delta 1, then the elongation is what? So you find that like FAD is equal to EA delta 1, right? Delta 1 over square root of 2 over L squared. All right. So that's basically this first Castigliano's theorem. Any questions on that?
Ali,
Yes.
if they asked for the force for like a diagonal member, which included delta 1 and delta 2, like for example, member 8, how would that affect the force?
Oh yes. So you see, you have to put this substitute this subtraction, right? So you have to calculate the elongation of the member like we did here, and then you substitute, for example, for let's say, which member was that? Like member 8, right? So f member 8 is equal to EA based on, okay, so here you can know the sign after you calculate delta 1 and delta 2, you know the actual signs of these two, right? So let's say you find out delta 2 like is greater than delta 1, and then you divide by L. So this becomes, so now these are known values for you, right? You don't need to assume anything. These are known values. Does that answer your question?
So just say that delta 2 is smaller than delta 1, then you get a negative value for like total delta. Does that mean that the force in 8 is a compressive force?
Yes, exactly. So you see, for example, if I have this member, so this is delta 1, right? And this is delta 2. So let's say delta 2 is 0. Delta 2 is 0. So this is in compression, right? So delta 2 minus delta 1 is going to be negative here. So this gives you compression. Does that make sense?
Yes, thank you.
Yeah, sure. Other questions? Okay, I mean, since it's recording, I'll continue like 10 more minutes and just solve the third one, and then we're gonna be done. And like study for the final before Saturday or Monday, and if you have any residual questions, you can like go over them in the office hours, right? So, all right. So again, like this is the unit load method. So the first step is solving the actual structure, right? So this is the unit load method, and we want the rotation at E. Rotation at E, right? So the first step is solving the structure, right? Solving the structure. All right, so you find the reactions first, right? So this is gonna be P here, this is gonna be P here, and this is gonna be P. So these are the reactions, right? So you can be smart about like where you take coordinates for these frames when you want to like calculate the moments. So we have to get the actual moments, right? So this is A, this is B, this is C, this is D. So you use the cut method, right? So the cut method is probably the best. Like you bring this out. So if I bring out the cut, so there's going to be P, there's going to be P, and this is X. So, and I want this moment, right? So MAB. So MAB is PX. And like your coordinate is like this. This is X, this is Y. Right? So, okay, so because there's E, and I know that in the unit load structure, there's gonna be a discontinuity here. So you have to like do some extra stuff at E. So for E, I take my coordinate like this. So you make a cut here. So if you bring that out, so this is your cut, this is X, this is gonna be P, this is gonna be P. So you just take the moment about this point. So this is gonna be MBE. So MBE is equal to PL minus PX. Now your coordinate is like this. All right, so for the right of E, I can take my X from here, right? Make a cut here. So if I make a cut at this point, so this is gonna be M. I call it MCE. right? So there is one P here. MCE is going to be PX. So that was my analysis for the original structure. That's it. So you have the moment everywhere. Oh, there's one member remaining, which is like DC. So you need one cut also here. So if I make a cut, so it's going to be like this, right? This is P. So MDC is 0, which is good. So now the unit load structure is something that many people got wrong, unfortunately. So you want the rotation at E. I've seen people apply forces. So you want the rotation, right? So when you want the rotation, you apply a unit rotation, a unit moment. So this is one. So again, you have to repeat the analysis for this structure, right? So if you take the moment about this point, you get 1 over L for this one. So we get 1 over L, and sigma of x is 0, so this is 0. So this one is 0, right? Okay, so you see A, B, C, D. So again, if you have to use the same coordinates that you used before, that's very important. In the unit load structure, use the same coordinates as used in the, basically by coordinates, I mean just you make the same cuts. Make the same cuts that you made in the original structure. So here I make a cut again like here, then you find that MAB is 0. MDC is 0. How about this cut? So again, you make a cut like this. So this is 1 over L. Now you have this tiny MBE, right? And this is X. Oh, so Brian is asking about the unit of 1 over L. Okay, so you see, the thing is, this one has a unit. This one has a unit of force. So basically, it's force over displacement, right? Yeah. It's force over length. Sorry, it's moment over length. So you see, this one has a unit of moment, which is, let's say, Newton meter. So here you have Newton meter over meter, which is Newton, which is force. Nice. So basically NBE is negative X over L. So I make a same cut that I made before for the right side. Now I have X, I have 1 over L, I have MCE, right? So MCE is what? X over L. So again, like the formula is the same. Now you don't have any temperature or anything. 1 times theta is equal to integral M over EI. So you see, if capital M or lowercase m, one of them is 0, you don't need to integrate over that part, right? So I just need to integrate over BE. So basically, the only part that both of them are non-zero is this part and this part, right? So the moment diagram looks like this for the unit load structure, right? So this is plus half, this is negative half. Negative plus. So this becomes 0 to L over 2. This is for BE. Becomes, so you put the capital M, so BE, it was PL minus PX, right? PL minus PX times negative XL over EI plus integral 0 to L over 2. So for CE, it's px. Remember that I used the same cuts, the same x's, the same cuts in both the unit load structure and the original structure. So this will be x over L. And that's it. After you calculate these integrals, you have theta e, right? I think that was a good problem. All right, so yeah, I'll have a couple of more office hours, like try to study for these materials. And today I'll not have the office hours, but I'll have it on Saturday and Monday because I want you guys to like make sure you have studied before the office hour. Yeah, it's gonna be the same online thing. I'll send you the times over email. And that's it for today. Yeah. Good luck with the finals week. All right. Thanks, guys. Bye.